Alright, making a video. Draft physics video presentation. Alright, only one comment, so what the hell. Yeah, just get over with quickly. And then on to Van Biezen, hopefully, soon. Let's see. How do I not see this long-haired freak in my YouTube feeds? So it's kind of a stupidly phrased question because it could be taken more than one way. But anyway, yeah, it's too bad that YouTube feeds stuff. It's too bad I even see your comments. Unfortunately, I should be able to just select, for, yeah, no, don't bother letting the stupid people comment. People with dopey icons. But he calls himself Mr. Agnostic. First, to be proud of being an agnostic is, in my opinion, kind of evidence of your lack of any kind of real integrity. You're just kind of glib. If you don't know Winnie the Pooh is a lie, then in my opinion you're an idiot. I mean, if you don't know, it's not true. You're not sure whether there's a real Winnie the Pooh walk around, a stuffed animal with a brain and all that stuff. If you think there's some doubt that, oh yeah, maybe it's true story, then you're an idiot. And you're an idiot if you don't understand that God is implausible as a physical thing. There's no physics for it. It doesn't make any sense. The infinitely intelligent thing just always existed. Right? I mean, if they gave God a father, or if he had some kind of lineage and he evolved on some special planet, they were Vulcans or something, might be more plausible. But it's physically impossible for there to be this stupid God. And then on top of that, we know it's just a story made up by people, and that it wasn't even made up like by one guy who thought it up. We know it, changed hands a lot, the story, and that's just an old fable reworked. Old themes that are even older than the Bible, and just reworked, regurgitated same crap, rechewed beans or whatever. Gristle. And anyway, there's no reason to be agnostic on this subject. There's no reason to, I have to give it the benefit of the doubt. What doubt? There's no reasonable doubt. There's only unreasonable doubts. So you're an idiot. And he has this glib icon, and he has trivial videos, and he just insults whatever an agnostic might be. He's a poster child, so to speak, and claiming to be the mister of the subject, and he's a buffoon and an asshole, which just demonstrates, it doesn't make agnostics look good. just saying. So anyway, idiot. And this coming from a guy who has to walk around with a baseball cap because he's going bald. This is another point just to raise. So the old comment shows up, Zohar, Kanevi, something like that anyway. He did make a video, sort of explaining my physics, but frankly, I don't know if it's entirely my physics, but it's really nice. Can't hurt to have more people talking about it, so that's great. So link below to the video, but 209 views, not bad. He's got some sort of Discord thing going. I don't get the whole Discord thing. It's just, that's a gamer thing, I guess, or whatever. Typing arguments. Anyway, yeah, no, that doesn't appeal to me. I read the comments, but they're kind of trivial and not very smart. So, but the thing is,
arrows pointing in a direction.
So, yes. Anyway, so he does explain arrows in a direction, sort of. So anyway, the idea would be is that I might be doing some live rooms and just to sort of go over some of these basic ideas that apparently I haven't been able to explain in a way that seems like reasonable people can understand, which is a little disturbing. But it is physics, and so, yes, so that might be helpful to other people who I have likewise in some way or another confused. Because, yeah, although this is sort of my physics, it's really not, my physics. So, I mean, it needs to say what I think needs to be said is, there's some certain points that are kind of critical to understanding the differences, the distinctions that are missing. And so, anyway, we'll see how that works out. We'll see if it works out and such. So, but that's for another day or another time of the day. So, anyway, yeah, I don't want to change the subjects. I mean, I could re-explain gravity, but whole point is to make this concise and have the titles mean what they say, so to speak. So on the subject of light, though, so it does bring up a subject. I did see some mathematical videos explaining what happens when you put transparencies in front of the two slit experiment, which I thought was sort of an interesting, sort of useful to my purposes anyway. Gotta get this thing in the right place so I don't have to do this crap. I guess I could just slide that over the other way. Now I lost my piece of chalk. Alright, anyway, so the idea would be is you're doing a double slit experiment, and what you do is you put a different layers of transparency over one of the slits, a thin film or even thick pieces of glass. And you'll take basically the pattern that would have been, the bright here, and you'll basically migrate the pattern to a new position in space that is going to be off by, depending on what you're using as a, how much delay is kind of how they argue it. Like glass would delay the photon and cause a phase shift based on the delay of the light through one of the surfaces. But the point it really illustrates is that this pattern isn't created here at the slits, that the slits are in fact sending light to all the locations over here, and that all you're really doing, as I stated, is putting photons back together. And so when the phase is restored, that is when you're one full wavelength or two full wavelengths or three full wavelengths off in terms of the difference in the distance, you reconstruct the photons, because now the photons are back in alignment. So the argument is when the photons hit the surface out of phase, okay, in time, which is perfectly consistent with this quantized idea of the photons actually being little bits, and the little bits have to be in the right order. And obviously when you put them out of phase by one full wavelength, then they end up matching each other and being in phase. And that's so if one piece is missing a couple of these little lines, one there, and this one's missing this line here, when you add them up, as hitting a location, let's just get rid of these because we don't need these, you could see that they'll add up back into a photon. So when that fragment hits and this fragment hits, they'll have two bits in one place and only one bit in one place, but it'll be back to being a photon in the sense the frequency will be back. And that's the important part of the photon. So anyway, I think it just proves the point that there's nothing rigid about this wave mechanics. Now, their mechanics is still consistent in the sense that, obviously you can't duplicate this in any simple way with water waves. At least I haven't seen it done. And the idea is that, like I said, that this is a reconstruction and that there is no destructive interference in locations. There's just places where the photons are still out of phase here. So the pieces, the fragments you made by having the slit. So the idea is the slit is what's breaking the photon. Part of the photon hits the material, so only a partial piece of photon leaves. And the bright spots are where you're reconstructing a broken photon from one slit and a broken photon from another slit, or more precisely surfaces. The surfaces that are breaking the photons And so the more pieces you make, the more pieces you break off, the more fragments you have to put back together. Well, anyway, I just thought it was another demonstration of my theory being consistent with the evidence, which is all it has to do. And that it's a better theory, and that it's a rational description, a reasonable description of the physical mechanics versus some, magical forces are causing all of this, when you don't need a magical force to cause the effect. All right, so on to the Van Biezen and such. I guess I could just slide over a little. Oh, I don't know if that works all that well, but anyway, we'll try it for now. So we should be on Compton scattering. Now, Compton scattering is a little bit boring because the substance of it only happens to very very small effect. So you won't see it much in everyday life.
Welcome to electron. In our quest to understand what a photon is, we're now going to take a look at what we call the Compton scattering. So Compton had discovered when a photon would be approaching an electron, and if it approached it just right, it would be scattered by the proton in various angles depending upon the approach vector. Good way to say it. And what was interesting was that the amount of energy lost by the photon as it was scattered would depend upon the scattering angle. So here we have a little picture.
All right, so so this is a conservation argument, essentially. I think it could be said that way. Momentum has to be conserved in this process of light getting from one place to another. And again, the argument's going to be is that he'll demonstrate some of my argument for me, is that the photon is this thing spread over a large area in terms of it's going this way, these little bits of stuff, and it's going to encounter now things that are very small, okay, not very big. And so part of these bits will interact with these little things in the atmosphere, and they will, by some sort of precise mechanism, but anyway, they will be deflected in directions. They'll cause motion, the motion will cause other motion, however it happens, but the bits will fragment. And the point would be is that when that's happening constantly, it ends up being consistent in the sense that you keep your phase, because things end up having a probabilistic outcome of hitting a certain amount of stuff at a certain amount of times. And the end result will be is when you're actually measuring what you're getting back from the world, what's happened to the light as it passes, that you're going to be measuring these this effect of, again, different photons, and the fragments ending up hitting a surface, and the surface is going to say, yes, a photon reached the surface. But the surface that's collecting the photons is large, 1,000 atoms. The little atoms in between that it's hitting, the little bits, are obviously spread out over a large area. And again, this is just another example of recombining the bits, and the bits of the scatter are going to be in all directions to start with. And there's nothing much else I think has to be said. He's going to point out, like I said, some of the things that are important to point out, and you'll just see how kind of unrealistic what he's saying is by comparison.
We have an approaching photon. It's coming in contact, and I'll put that in quotation marks, with an electron, so that the photon would be scattered in one direction and the electron would then be scattered in the other direction. And the change in the wavelength of the photon, which means it would lose some energy, the photon would lose some energy, is equal to h divided by the mass of the electron times the speed of light times the quantity 1 minus the cosine of the scattering angle of the photon. So which means that if there was no scattering angle at all, for example, if the photon just continued on its merry way and was not affected by the electron, kept going straight, of course the cosine of 0 degrees is 1, 1 minus 1 is 0, and there would not be any change in the wavelength. On the other hand, if for some reason the photon approached the electron and was scattered in such a way that it returned back in the opposite direction, so that the scattering angle was 180 degrees, then 1 minus the cosine of 180, which is a minus 1, this quantity would become 2. We would then get a maximum value. In other words, there would be a maximum change in the wavelength of the photon if the photon was simply scattered back in the opposite direction.
So the odds are it's not going to be scattered back in the opposite direction unless the electrons are already moving. What he hasn't really talked about is this big giant wave, and that'll be part of the argument here. This wave of light, that is the polarization of the light, the thickness of the beam, is preposterously huge compared to the size of the tiny electron, like 1,000,000 times difference. And this idea that this wave is somehow interacting with the electron is totally unrealistic, that only elements of that wave could possibly interact with an electron, and that's where their theory doesn't make any sense at all. I mean, you can't have something spreading over thousands of atoms and then say that thing is affecting one single electron. Just totally unrealistic. Nonsensical.
And the other angle between 0 and 180 degrees would be some fraction between 0 and 2. It would be some quantity between 0 and 2. Very interesting concept, especially so when you start thinking about the difference between what a photon is and what an electron is. An electron is a very small point particle, roughly the size of 1 times 10 to the minus 18 meters, much smaller than the diameter of a nucleus. And a photon...
So let's understand that the change in frequency, this tiny amount of a change in its phase, really not so much, but anyway, would be caused because, yes, every time you change the force, that is, the force hits an electron, the electron absorbs it to move. It can't move unless it absorbs the force. So this is kind of, gets back to the gravity argument. You just sort of have to understand the difference between different ways of describing the fundamental function in terms of what happens when two things interact with each other. And, you know, they have this notion that it's some vibration thing and that the vibration from the photon goes to the electron and the vibration is absorbed and blah, blah, blah. But there's just no explanation of how you, how that vibration is held or maintained in the thing itself. So as I've attempted to explain, there's kind of a big difference between me saying a force hits something, the force disappears, it dies, like the photon would die, and this thing would move. Okay, and like as if the photon, you know, sort of connected to it and stayed on it, right? So it's like it got stuck, and now it could move the object, and that somehow something would collect momentum. You know, it would absorb it in the real sense of the word, in the sense that now it's moving, and the movement is because it's like a boat analogy, and say there's little motors in the water, and the little motors can stick to your boat and, you know, push you in different directions. Well, then obviously your boat would start to get kind of heavy, you know, because it's just collecting motors. It could collect a motor going that way, and then it'll collect a motor going that way, and it'll get thicker and thicker and bigger and bigger. And we kind of know electrons don't do that. They don't get different. They stay the same. No matter what happens, they're always electrons, and they can always be put back into their electron state. And so my argument is that, you know, what's really happening is the electron is an amount of energy that is neutral, but it has it inside of it, and then what it's going to do with the outside world is make an exchange. Something's going to go inside and something's going to be let loose, and that's conservational. And it also has this implication that this thing moves rather dramatically, in the sense that it gives back something going the opposite direction, because the odds are it's going to interact with an element coming towards it more often than an element going away from it. It's not going to be able to catch something going just as fast as it, certainly, and it's just more likely to hit stuff coming the opposite direction. So as a matter of probability, it's likely to give back something the opposite of what it's exchanging, and that means there's almost a 2x increase in its motion in that direction. Now it still has motion in other directions, it could, and so it's just added to the rest of the motion of the boat, but the boat never gets heavier. it just gets, as you make it go faster, it just ends up with more occupants, more rowers going the same way. And that accounts for its apparent increase in mass in the direction it's moving, obviously. But it's losing mass in all the other directions because these other arrows start to disappear as they get exchanged for this way. And so it's just a fundamentally different way of understanding interaction. This interaction or absorption is really exchange, and so you really still have this element is still in the universe going somewhere, so it's still real energy, and all you're really doing is changing the disposition of something else. And so it's still conservational, but I'm just saying it's fundamentally different than this idea of something hitting and being neutralized in some way, and then this thing just has taken it as a new bit inside of it. It's gotten bigger to accept a new bit of momentum. So the two ideas are fundamentally different. And I think it's a sort of an important difference, because I don't think you can do magnetism and all the other things that go on electricity with this idea of actually absorbing the energy without giving back, without the reflection. It's critical to the function of repulsion. So my argument is repulsion in atoms between charges is basically the idea that this little bit is going back and forth, and that each time it goes back and forth it has this perfect reflection where it's absorbing a force in the opposite direction. So this direction goes in and this direction comes out, so to speak. And the same thing is happening here. This direction goes in, this direction comes out, and so this ends up being maintained as a pressure. And obviously the implication is as that pressure keeps hitting, every time it's hitting, it's changing the disposition of the stuff here, giving it more arrows in this direction away from each other. And that's why the objects move away from each other. So it's sort of an important difference in terms of recognizing how energy is absorbed. Quote unquote. Absorbed.
Comparison, even a very high energy photon like an X-ray or gamma ray photon is huge in comparison. The wavelength of a photon is much greater than the size of an electron. So you might wonder, how can a photon, which is a particle, an energy particle so to speak, collide with an electron and be scattered by it? It's not like there's a physical collision like between two billiard.
Right, so this part they're just making it up, right? So they're just trying to make up some explanation. And it's lame, and it's all just made up. You talk to a different physicist, they'll come up with some kind of different way of trying to explain it, but it's lame, okay, in the sense that they're saying this big giant wave, somehow the entire wave is interacting with one single electron, which is just a ludicrous on its face. The thing is thousands of atoms thick, dispersed over an area of thousands of atoms. It's dispersed. And it's supposed to be hitting this, it's supposed to be interacting with this point particle that they won't even give volume to. It's so infinitesimally small, it doesn't even have a volume. And yet somehow this gigantic wave is interacting with that one single tiny little bit. There's no way to make that reasonable. Their theory's obviously incomplete at minimum and catastrophically flawed as the reasonable maximum. I mean, there's nothing good about this part of their explanation. It's just an indication of you probably have the wrong answer because you really can't explain this reasonably. There's no reasonable explanation.
Balls, for example. But what's happening is, since a photon causes a changing electric field, the changing electric field as a photon zips by the electron at the speed of light, which is 186,000 miles per second or 300,000 kilometers per second, while it's zipping by at very high speed, that changing electric field of the photon causes a change in the electron, because the electron is a charge.
So yes, right. So now we're saying that this big giant thing is affecting a field in a big giant way. So that this still doesn't make any sense. Well, then why wouldn't it affect every single electron within that whole field change. So now you're taking something that's really huge by comparison to the tiny little dot. You got this big huge thing compared to this little thing, right? Got this little thing, got big huge thing. Then you're saying this big huge thing is oscillating a field somehow outside of its dimension. It'd have to be outside of its dimensions, right? Oscillating this field, and now you're saying it's still only affecting this one little piece of chalk. No, it would affect every single piece of chalk within that area of that field if you're going to make this argument. So again, there's no coherency to this explanation. It is incoherent to its own stipulated facts. Tiny point particle with no volume interacting, one single bit of that interacting, and there's just no explanation for why it doesn't make every single electron move.
Particle, which would then feel the effect of the changing electric field, and because of that, there would be an effect. There would be a scattering effect of the photon and the electron. And momentum will be
so no explanation of this scattering effect, because there's no explanation of any angular momentum going in. There's no field going this way or field going this way. There's just nothing, no explanation for why there would be a scattering difference between how the field interacts with the tiny point particle. So again, the field change is huge, the particle is infinitesimally small, and again, yet they're saying that there's some possibility of having all these scattering angles. How could you possibly have scattering angles when your wave doesn't have any point of direction? It's an oscillation in a field going like this. It's a perturbation, okay? So it always has the same direction, up and down. It doesn't have any direction in any other field.
conserved in the collision, and also energy will be conserved in the collision. We'll look at that at a later video. So what we need to see here is that we have three parts of this equation. We have the left part here, which indicates the change in the wavelength. This would be the final wavelength of the photon leaving that event. This is the initial wavelength of the incoming photon. This quantity right here is only dependent upon the mass of the particle that we're colliding with, or that the photon is colliding with. This would in this case be like, say, the mass of an electron, but it could also potentially be a proton. H is a constant and C is a constant. This is Planck's constant, this of course is the speed of light. And now this quantity here is just simply a number that's dependent upon the scattering angle. Since this quantity over here will be a constant if we're dealing with a...
So again, you could argue that this is, you know, well, there's lots of things argued about the motion and how regular the motion would be in any one direction. And again, the readmission of a photon. So the basic argument is that the scattering angle is a byproduct of what happens to the thing you gave momentum to. It loses the momentum, and in losing the momentum is when it's giving back the photon. So it's giving back the energy in rebounding to some other position. Again, even in an atmosphere, these little particles have a place they want to be, and you're disturbing them, and they'll tend to go back in some direction that's more comfortable. But it's the going back, it's the giving back the energy. It has to give back the photon. It can't do both. And they're trying to make an argument, see, because they've turned this all into mathematics. They're saying that the momentum of the electron has consumed some portion of the energy of the photon, when it really hasn't, because they think energy is frequency, and the frequency isn't its energy.
particle, in this case electron. And this quantity right here is simply a number between 0 and 2. That means that the change in the wavelength is simply a function of the scattering angle. And irregardless, and this is the interesting part of it, I think, irregardless of the wavelength of the incoming photon, the difference will always be a constant value depending upon the scattering angle. So it doesn't really matter if this is a very high energy photon coming in, like a gamma ray or X-ray photon, or maybe a visible light photon. If there's any sort of interaction, the change in the wavelength will be a constant value, only dependent on the scattering angle and the mass.
All right, so we have again an example of where they're saying interacting with electrons causes a change in frequency. And yet these are the same people who will conclude that nothing, the light coming from the rest of the universe, is redshifted. And their explanation for that redshift is because a bunch of space got injected. when clearly the explanation could be that the very process he's talking about has retarded or stolen some energy from the light, that is, redshifted it, made the wavelengths longer by having one of these interactions with a tiny bit of an electron. So he's basically saying electrons can cause a phase change, a frequency change, a wavelength change. That's what he's saying. And yet they don't put those two and two together. They're not obliging that truth to be a truth for the rest of the universe and have the obvious understanding that, well, then obviously light that travels further distances through space would likely have more interactions with little particles in space, be Compton scattered, and therefore be redshifted, because they can only lose energy. The photon can only lose energy from the interaction, and therefore redshift. I mean, they don't put these two, these are stated to be, so again, you have two different theories for why there's redshift. One theory is this Compton scattering, the other theory is space is being injected. Which one is true? Which one has more hope? Well, I clearly say this one has more hope, but it's really just a consequence of the fact that to move an electron, electrons move much slower than the photons move, and therefore there's every probability that you'll create a frequency change because some of the time is being absorbed by the electrons moving. And when the photon is clearly interacting with individual different, every bit, every quanta of the photon is interacting with a different electron, then you can understand that the average motion of the electrons is now going to be the thing deciding how they're going to be readmitted, and in what order and at what frequency.
Particle, not on the wavelength of the incoming photon, which is really strange in a way, but that's what we found it to be true. The reason why we know that is so, we had put detectors on there. So what we had done is we had kind of put a detector going around like this that could move in different angles, and so we could actually measure the incoming or the scattered photons at various angles. We can measure the wavelength or energy of those photons. We would have a given set of photons coming in at a given known wavelength, and so we can then actually measure the energy and therefore the
he didn't really state it in that drawing, but what he's basically saying, to clarify, is so they shoot light into a substance that would have small particles in it, a beam, I guess, of some kind of known, something that isn't already dispersed. And the particles are in here, the electrons. And when he says we measured it this way, well, it's essentially the same as a flat screen, except you get a more accurate result measuring it this way. And they're just taking the scattering angles, okay, that light that hits, that's dispersed by the little particles as you would expect it to be. And the argument is that the light that hits here, the wavelength is a little bit longer, less long here, so it's more red here, a little less red, a little less red, and its original color here. So no matter what they put in, no matter what color light they put in, they get this same proportional relationship of the sharper the angle of the dispersion, and I suppose they could go all the way back here, the more shifted the light is. And there might be a difference on this plane, as I would argue there would be, okay, and that you're not going to get the same effect over here, but who knows, on the rebounded light, the reflected light, versus the light that's scattered. But anyway, so that's the idea. But this is a tiny difference. So let's understand that too. That this isn't something you could. This only works on like gamma rays, where you see enough of a difference, where you could actually see some of this redshift. But you could understand that if I created a dense enough field of this stuff, and there was enough, I was creating even more scatter. Let's see, or a better way to say that. More of this stuff causing these kinds of scatters, but having the same scatter happen again and again and again and again. So, well, anyway, that yes, I could redshift it more. I just need a strong enough beam to be able to survive that many scatters, which you could argue the light coming from a distant sun through space is probably evidence of something like that. So anyway, continuing.
The wavelength of the scattered photon, and we discovered then that this was the equation that met the data that we measured from that experiment. And of course, this was constant who did that experiment. So
so there's really nothing to this equation, right? They just have a factor here that tells you what this arc is, where you would be positioned on this arc. That's the 0 to 2 number. It's just telling you how dramatic your arc is, how much scatter there was. And the higher that number, so this would be like, I guess a 2 might be back here, and then you would go all the way to 0 here. And so it would be 0 to 2, and that tells you how much a change in the wavelength there is. And the rest of it's just constants.
Interesting that there's no dependency on the incoming photon. So what we're going to do now is calculate these various quantities. So let's calculate this quantity for an electron. So for an electron, we can say that H over mc is equal to 6.626 times 10 to the minus 34. That would be joules times seconds, divided by the mass, which is 9.
So the only thing this has to do with is they're basically saying the bigger the particle, that is, the heavier it is, the less momentum it has, the slower it's going to move, and the longer likely it's going to occupy the motion before it rebounds. The rebound speed is going to be slower for a big particle than a light particle. I would argue that that's one way of looking at it.
0.11 times 10 to the minus 31 kilograms, and the speed of light 3 times 10 to the 8 meters per second. So what would that quantity equal? So let's find out with a calculator. So 6.626 e to the 34 minus, that would be divided by 9.11 e to the 31 minus, and divided by 3 e to the 8, and we get a quantity of 2.42. So it would be 2.42, that's good enough, times 10 to the minus 12. And remember that the units would be in units of wavelength, that would be meters. So it would be 2.42 times 10 to the minus 12 meters, which is 2.42 picometers. Notice that it's much, much smaller than the typical wavelength of a photon. Now, this quantity here...
right, so it's a tiny 2 picometers, okay, which is, 1,000th of a nanometer, right? So, you're talking about, a change from like light that would be at 500 nanometers would be at 502 nanometers, something like that.
A number between 0 and 2. If the scattering angle is 0 degrees, then the answer would be 0. If the scattering angle is 180 degrees, that would be a 2. That means that this would then vary in a range anywhere from 0 to twice that number, so I multiply times 2, and I get 4.85 times 10 to the minus 12 meters. So that means that this quantity right here would be a number anywhere between 0 and 4.85 times 10 to the minus 12 meters, which means that's a change in the wavelength of the scattered photon. And since that number does not depend on the wavelength of the incoming photon, lambda sub tau would be the initial wavelength of the incoming photon, that if this is a photon with a very large wavelength, let's say the wavelength of visible light, 500 times 10 to the minus 9 meters, this change would be so minuscule compared to that, we could not see or measure that effect with photons of visible light. We can only measure that with photons that are comparable in size, such as X-ray photons, which may be 100 picometers or 500 picometers in length, in wavelength. We can then see that change. It would be subtle, but it can be measured. But for something as large as visible wavelength, there's no...
So a picometer might be 1 million nanometers. I don't know. So he's basically arguing we can't measure it with visible light. I don't know.
Specific effect in the constant scattering. So that means that when the wavelengths are even much bigger. Now here I drew a wavelength, even though it seems very large compared to the size of an electron. Imagine a wavelength of a photon of visible light. That may be as big as a freeway. Imagine the size of a freeway and putting a small little grain of sand on the freeway, and imagine that the freeway is the photon and the grain of sand is the actual electron. And you can see when the photons are really big, the effect on the electron between the electron and the photon would be virtually nil. That means
so, an argument doesn't really make any sense that somehow this giant wave is not creating a substantial amount of space that's being interfered with, and that somehow if I cut it in half, I've somehow fixed that problem. And you haven't fixed the problem that your point particle is minuscule compared to the polarization of your wave, the diameters of it, the volume of it, the dimensions of it. And there's just no explanation for how that big giant wave affects one tiny electron and doesn't affect all the others.
Means that the change in the wavelength could not even be measured. But if the photon becomes much smaller in relationship to the size of the electron, still very big, but much smaller than the Fourier wave, of course, then you can see that there would be a much bigger effect, and so the change in the wavelength would become a larger and larger part of the wavelength of the incoming photon, and therefore the change in the energy of the photon, because the energy, of course, is related to the wavelength, the change in energy would also be much.
So again, is related to the wavelength. It's not the energy. Again, this is just the tipping point argument. The only thing that makes high intensity photons, or this idea of frequency, matter is the fact that it's a tension argument, it's a trampoline argument. You can't, you have to push electrons out of their glue, and to break the glue you can't hit it slow and let it rebound. You have to hit it while it's moving away and keep hitting it to move it away. And that's it. It's not a pure energy argument, it's a circumstantial energy argument. It's only because of the circumstance that electrons are bound to something that this argument can mean anything, that frequency can matter.
Greater an effect on photons that have a much higher energy than for the ones that have much lower energy, but in other words, much smaller wavelengths versus much larger wavelengths. So again, we're trying to understand what a photon is in how it relates to the different interfaces or interactions that it has with other properties, with other things such as electrons.
Yes, with other things that you don't give any volume to. So it doesn't make, again, their argument doesn't make any sense. They'll say it right to your face that the electron is a point particle, that it has no physical dimension, as far as they could care. It's infinitely small. And yet it's interacting with something that's definably huge by comparison. And that makes sense to them, when it can't make sense.
Electrons and protons. So when a photon collides with an electron, and collide, of course, is kind of a strange term, when it interacts with an electron,
Right, and it's only a strange term because they don't give the quanta any reality. They don't understand that a photon is actually a collection of little quanta bits at a distance from each other, and at a distance out of alignment with each other. Parallel course. They're running the same vector, parallel vectors, out of alignment. So it's just like me shooting a gun by moving the gun up and down. The bullets are going to be going in the same direction, and if I have a consistent rate, they're going to have a consistent distance between them. And the bullet argument works. It explains the interaction. It explains why that big giant wave, right, this whole row of bullets, it explains how a bullet can interact with an electron, one of the bullets, and that another electron can react with one of the other bullets, and all the bullets can interact with electrons in different places and have their frequency and their phase changed by that experience and be recombined at some output where all those bullets still have to go somewhere. And so you still collect all the bullets, and you'll collect some of the frequency and some of the phase. You'll get back some of what you shot as a pattern. The pattern will survive the experience. It just won't be as complete as it was when it started.
the wavelengths are very small of photons. There's a real interaction that can be measured. If the wavelength is really large compared to the electron, it's an unmeasurable interaction. But what would it be if instead of an electron, that was a proton? What would the effect?
Well, let's understand. It's not an unmeasurable. It's just the fact that you're not going to see that tiny. It's only a tiny bit of change the electrons can make. So again, this sort of reinforces my argument, is that the bullets are interacting. And so each bullet just causes a certain amount of distance that you can get out of the bullet. So it doesn't matter how I change their frequency or I change their polarization. Each individual bullet's doing the interacting, And so with a big wave, you're talking about a tiny difference. And obviously when I make the waves, when I make the period closer and closer, the tiny difference becomes more and more because I have a smaller distance. So 1 millimeter out of that distance is a big thing, where 1 millimeter out of that distance is a small thing. So it's just the measurability. It's the same amount of change because they're solid bullets. The quanta are doing the interacting. And the quanta can't do more than a millimeter of difference because it's only a bullet. To them, it's one bullet. To them, it's one amount of movement, one amount of distance at the speed of light. It's a quanta to them. And so all you're saying is that, yes, it's harder to see a millimeter in here than it is to see a millimeter in here.
Be then. So let's try that. So now let's say that we have a proton, and now we're going to calculate the h over mc, so the Compton scattering with a photon and a proton instead of a photon and an electron. So this would be 6.626 times 10 to the minus 34, that's joules times seconds, divided by the mass of a proton would be 1.67 times 10 to the minus 27 kilograms, and multiply times the speed of light, 3 times 10 to the 8 meters per second. And let's see what we get this time. So 6.626 e to the 34 minus, divide by 1.67 e to the 27 minus, and divide by 3 e to the 8. And there we get 1.32 times 10 to the minus 15. So 1.32.
So a much smaller change.
Meters. Notice this represents the portion that determines the change in the wavelength. And with a proton, the change in the wavelength would be much, much less than when it interacts with an electron. And again, using the same scattering angle concept here, that would be anywhere from 0 to twice that much, so this times 2, so we get 2.65.
So you could sort of understand that as the little things, the electron can move more distance before it gives back the photon. Because it's smaller, it's more momentum to the electron. And the proton, because it's heavier, the amount of rowers you're replacing is bigger. So if you have 100 seats in the boat and you jump in and row in a different direction, you're going to sort of understand that the 99 are going to dilute your effect more than if there's only 10 other rowers in the boat. Then your effect is going to be much greater. And that would be the difference between the proton and the electron in terms of having an effect on frequency would be proportional to how big an interaction it is, and how big one little quanta of light hitting an electron or a proton, well, the mass of the proton will consume that momentum and dilute it a lot more than it will be diluted by the electron. And that's proportional to the change in the wavelength of the readmitted photon.
5 times 10 to the minus 15 meters. So even with a very high energy X-ray photon, you could not measure the scattering or the change in the wavelength due to the scattering, the Compton scattering, when the particle was a proton instead of an electron. So Compton scattering is something that we can measure when we use electrons. When we use protons, it's virtually nil. So what is the difference between the interaction between a photon and an electron and a photon and a proton? A proton, of course, would be much bigger. A proton would be something like this in relationship to an electron. And yet, the interaction is such that the scattering angle would cause virtually no change in the wavelength and therefore no change in the energy of a photon.
I would argue that the photon is electron energy. That's why it's electromagnetic. It's because it fundamentally affects electrons differently than it affects protons. And so the difference probably has more to do with the fact that it's not reflective energy. It doesn't do the same, it's not the same kind of exchange. But anyway, that's a whole nother subject.
Well, part of that may be that the necessity of the conservation of momentum plays a role in this. The reason is because when a photon hits an electron, it bumps the electron and it goes off, speeding off at some high velocity because of the conservation of momentum. But the proton is so large when a photon hits it that there can't be much of a change in the momentum of the proton and the change in the energy of the proton, which would be 1/2 mv.
So again, their argument is that the photon comes in, the new photon leaves, and the electron moves. And to me, that's the wrong stage. So basically, their argument is that you can have both effects instantaneously, and you don't have both effects. The photon is absorbed, the electron moves and then it re-emits the photon. So they have this Feynman diagram sort of wrongly written. It doesn't happen that way.
Squared, and so therefore the change in the photon then necessarily would have to be very small because that large particle would be so difficult to move. So again, it's interesting how even at the quantum mechanics state, the interaction between photons and particles give us a visibility into what these particles might be. So hopefully this helps us again get a little better understanding.
Right, so there's no understanding provided at all, really, because there's no way this giant wave affects this one tiny electron. You have to put it in, they have to do quantum mechanics, and they're not doing it here, right? This is sort of described as something to do with particle physics and quantum mechanics, but there's no quantum in here. There's no talk about the wave, the ray length, there's no talk about the volume, there's no conversation about the fact that this wave has to interact with more than one electron. There's just no way it can react to as a direct entity where the full amount of energy of the photon goes into one electron and one electron releases the full energy of the photon. No realistic prospect that that's what's happening. Yet that's what they're asserting.
Of what a photon is in the way it interacts with electrons and protons in the Compton scattering. And that's how we figured it out.
Yeah, that's how they figured it out. They didn't figure, they're just making explanations, and like I said, they figured out a simple relationship. So let's understand, they shot light in, they collected what came out and saw that there's a frequency difference between the light that was scattered a lot compared to the light that was scattered very little, and reflected. And so that's all that this represents. This is barely a mathematical formula, and yet they're selling it as if this was some great insight into the function, when all their explanations of function make no sense. Giant wave affecting tiny point particle that doesn't have any dimension through the mysterious force of the electric field, whatever the hell that is, this magical field thing that only affects one electron at a time. So two electrons can be right here next to atoms, right next to each other. Somehow the field that this giant thing is creating, somehow that giant field affects this electron, but it doesn't affect this one, right? So this one's getting all irritated by this field thing, and this one's just sitting there saying nothing's happening here. There's no continuity to this explanation. It has no logical consistency. You can't step A, step B, step C. This is underwear gnome physics. Okay, and yeah, it's a joke from South Park. They got the A, they got the B, they got no C. Okay, steal underwear, make billions of dollars. So they got the A and the C, right? Steal underwear, and then C is make millions of dollars. But there's no B. There's no explanation of how you make billions of dollars stealing underwear. It's a good joke. But that's this physics. It's that bad. They don't have the ducks in a row. There's no A, B, C process to this reasoning. Okay. That's all I can say. Again, all I can do is reason with you. Can't do anything else. I have no other tools at my disposal. So I think that's enough of a video. So we'll see. Like I said, might be doing some overview style videos where I'll attempt to explain it to a believer, somebody who tends to get it, but what he's gotten isn't quite the right thing. But anyway, we'll see how it goes. So till the next time and such. It's enough.